Okay, so it's my great pleasure to introduce Professor Yann LeCun for tonight's A-Talk. Yann originally comes from the region around Paris. He did his electrical engineering studies here and received his PhD degree from Pierre-Marie Curie University. And afterwards he moved to Toronto to join Jeff Hinton's laboratory for a postdoc, and afterwards joined the AT&T Bell laboratory, where he worked on a number of important contributions. For example, he worked on convolutional neural networks. And in 2003, he joined NYU as a professor, and later became the founding director of the NYU Center for Data Science at NYU. And in late 2013, he became the director of the Facebook AI Lab, and remains part-time with NYU. And he's one of the leading figures in the deep learning movement. And so tonight he will speak to us about deep learning and the future of AI. So please welcome me in welcoming Yann LeCun.
Thank you. Thank you for this nice introduction. It's a pleasure to be here. Of course, I've known about Aldebaran for quite a while, and knew about the NAO and everything. But it's really interesting to see what's going on here. So I'm going to talk about machine learning, deep learning, a little bit about the past, a little bit about the present type of research, and about the future, challenges for the future. And I'll start with the past. So going back a long time in the history of machine learning, perhaps one of the first learning machines, the perceptron, from 1957. And the reason I'm showing this picture is because a lot of the machine learning algorithms that we use today are direct descendants of this. But also there are big differences. So the perceptron is a very simple machine that has some sort of sensor, some sort of feature extractor. It looks like a kind of a spaghetti plate here. And that's the classifier. And it was actually a piece of hardware. It was not a program on a computer. It was actually built physically. And it's very simple. Each of those modules or rows of things here are actually weights that linearly combine features that are extracted by this this feature extractor here, and compute a weighted sum. If the weighted sum is larger than a threshold, it's one class. If it's below a threshold, it's the other class. And the learning algorithm modifies the weights in that weighted sum. Nowadays, so the learning algorithm is super simple. I wrote the formula. You don't need to understand it, but basically it's error correction. You show a pattern, and if the answer is too low for the desired category, you increase all the weights whose input is positive and decrease all the weights whose input is negative. And then if the output is too large, you do the other way around. And nowadays you can program this in just about 3 lines of Python. So it's a lot simpler, but it's supervised learning. So supervised learning, you have a sequence of training samples, inputs and corresponding desired output. So for example, you want to do image recognition. X would be the pixels of the image, and Y would be the category. Is it a car, a table, or elephant, or a giraffe, or something? And then you have a number of examples, and you show those examples to the machine. If it gets the right answer, you don't do anything. If the answer is wrong, then you correct those parameters. So conceptually, you can see the architecture of the perceptron as, you take an image, you run this image through a feature extractor, which is built by hand. Those wires were actually built by hand, but nowadays we, or at least until recently, we wrote programs to extract relevant features that are important for a classification. And then this list of features, think of this as a vector, would be fed to a simple trainable classifier. For example, a linear classifier as the one I showed for the perceptron, but there are other types. So that's the standard model of pattern recognition since the 50s. And until very recently, that was pretty much the only game in town. And so conceptually also, you can see the process of training a machine with supervised learning as some sort of minimization of some cost function or objective function. So you can see the learning machine as kind of a function whose input-output relationship is determined by a set of tunable parameters. Think of them as knobs, all right? And you try to find the combination of position of those knobs that minimizes the average error between the output that the machine produces and the output you want. You can think of this conceptually as minimizing a function, this cost function averaged on the training set with respect to those parameters. It's just function optimization. People use something called stochastic gradient descent, which I'm not going to go into, but basically it means show one example, give the machine the desired answer, and then tune the little parameters a little bit so that the error decreases. And it's a very noisy process, but it's quite efficient. So the big question there is how do we how do we build complex machines, if you want, that can solve this problem? And the other big question is, this handcrafted feature extractor is where all the knowledge about the task resides. So a lot of the things that we know about the task we're trying to solve, image recognition, speech recognition, whatever, goes into building this module. And so if we and so that involves a lot of engineering, and a lot of publications in AI, pattern recognition, computer vision go into the design of those feature extractors. So one of the big questions is, I'm going to train this machine to classify, say, cars, airplanes, and other objects, and maybe chairs. Maybe it's going to learn to classify correctly the examples I use for training, but what is it going to do on examples it's never seen before? There's a lot of variability in the shape of chairs, and I can't possibly show all possible chairs to my machine when I train it, so what is it going to do when I show it a chair it's never seen? So that's the problem of the generalization ability. That's really the big kind of theoretical question for machine learning. And it's kind of, there are theoretical results that shows that machines under certain conditions can actually do a decent job on images they've never seen before, examples they've never seen before. Okay, so in reality, in the kind of modern machine learning systems, particularly the deep learning ones, we have machines that have hundreds of millions of adjustable knobs in them, parameters, like the weights in the perceptron. Very often we need to train them to classify thousands of categories. We can use millions of training samples to train them, and each recognition takes billions of operations. So the big neural nets that we use these days are pretty complicated, and some of them require a few billion operations just to compute the output from the input. Not something you can do on a Atom CPU, right? You need some sort of GPU or something like that to do this in any reasonable speed. So it's a very, very large scale optimization problem that we have to solve. And that, of course, comes with basic problems. Okay, so this basic model of pattern recognition, which has been kind of dominant until very recently, is being completely transformed nowadays with deep learning. And the idea of deep learning is you build your machine not by a fixed handcrafted feature extractor followed by a simple classifier, but you build it as a cascade of modules, all of which are trainable. So you feed the pixels, the raw pixels of the image to a module that you can think of as kind of a low-level feature extractor, and it's going to transform those pixels into some sort of slightly more abstract and high-level representation. Maybe it's going to detect simple motifs on the input, and then the combinations of those motifs will be used to detect higher-level configurations, parts of objects and things of that type. But the point is, all the layers are trainable. So we sometimes call this, we of course call this deep learning, but sometimes it's called end-to-end learning, in the sense that the entire chain of processing is trainable. That's really all there is to deep learning. It's deep because there are many layers in it. And so why does that work? It works because the world is compositional. What that means is the natural images are composed of basically combinations of objects, and a scene is kind of a combination of objects. And then objects themselves have parts, and parts are formed of elementary features, maybe contours or textures and things like this, and ultimately pixels. And so there are ways to describe an image that's kind of hierarchical, where you go from pixels to edges to motifs to parts of objects, etc. And so the depth of the architecture essentially captures this compositional nature, where the low-level detectors will detect very simple motifs like oriented contours or color blotches, and then those combinations of those are assembled to detect things like circles and corners and gratings and various other things. And then combinations of those are learned to detect parts of objects, etc., right? So that's what makes the world understandable, the fact that it's composed of combinations of simpler parts, essentially. This kind of compositional nature, hierarchical compositionality is not just true for images, but it's also true for text, for speech, and for just about any natural signal that you can think of, for actions, for just about anything. It's just what makes the world understandable. Otherwise, it would be completely kind of random. It would look random to us. And if you look at the architecture of the visual cortex, it's very much hierarchical as well. In fact, a lot of the architectures I'm going to tell you about are inspired a little bit by the architecture of the visual cortex, very loosely, but a bit. And so to recognize everyday objects, simple objects, the signal goes from the retina to the lateral geniculate nucleus, and then the back of your brain where the sort of primary visual cortex areas are located, and then kind of goes all the way up to the sort of side of the brain, the infratemporal cortex, where object categories are represented, regardless of where they appear in your visual field and what position they are in and things like that. So it's very much hierarchical as well. It's got multiple layers. It's very, very fast. In the human brain, the process of recognizing everyday object takes less than 100 milliseconds. There's barely enough time for spikes to travel through those various areas to get there. So there's probably very few effects of feedback and reasoning and things like that to interpret everyday scenes. But it's hierarchical, there's no question about it. So so this idea of using multiple layers in a learning system, of course, goes back a long time. Already people working on the perceptron had the idea that the salvation was in using multiple layers. But the problem is how you train them. And so that idea came up, became popular. The one solution to this problem became popular in the mid-'80s. It had been proposed before, but was kind of ignored. But around the mid-'80s or late '80s, people figured out there was a relatively simple way of training multi-layer networks, and that's called the backpropagation algorithm. So a multi-layer net, conceptually, is a network where you take a vector multiplied by a matrix. So it's a very kind of simple linear operation. And then pass the result, the components of the result, through a nonlinear function. In modern neural nets, this nonlinear function is what's called a half-wave rectifier, or sometimes called a ReLU, that stands for rectified linear unit. So it's very simple nonlinearity, kind of a thresholding operation, if you want. And then the next operation is, again, you take this vector. So many of the components will be 0 because they'll be saturated by this function, multiplied by a matrix, and then you get another vector which you pass through this function. Each component is passed through this function, and you repeat that process. And that's a deep neural net. Now, how do we train this? Well, so we want to train the coefficients in every single matrix here. And the way that's done is, basically we use the backpropagation algorithm, which I'll talk about in just a minute. But the way that those systems are built now, there are kind of frameworks, languages, some of which you may have heard of, Torch, TensorFlow, Theano, there's a bunch of them, to build networks of such modules. So the linear module is the one that multiplies a vector by a matrix. The ReLU is the one that does this nonlinear transform. There are other modules to compute distances between outputs and of the system and the desired outputs and the various types. And you do this by just assembling, adding modules to kind of a container if you want, and then deciding on a cost function and having a training set and a test set, etc. So the backpropagation algorithm is a very simple method that consists in essentially figuring out in which direction should I tweak each of the parameters of each box in such a way as to reduce the error for this particular sample I'm looking at right now. And it's basically a practical application of the chain rule, règle de dérivation des fonctions composées en français. So chain rule is just the idea that if I know how changing a particular variable here will affect the cost function, which is represented by this gradient vector. So this is a vector of the same size as this guy coming out of this box, which indicates for each component of this vector how the cost function would be affected if I change the input by a small quantity. It's just, it's a gradient. So if I know this vector gradient with respect to the output of a module, I just need to multiply this by what's called the Jacobian matrix of this box, which is the matrix containing all the partial derivatives of every output of the box with respect to every input, to obtain this vector, which is how this guy would affect the cost function. And so I can backpropagate those gradients all the way through, and with a very simple kind of basically automatic procedure, as long as I have the graph of the modules and that every module knows how to multiply a gradient by its Jacobian, I can propagate the gradients. I can also compute the gradients with respect to the internal parameters of that box, and that allows me to compute the, how to change all the parameters, all the knobs. So basically, I can very easily compute, in which direction and by how much should I change all the knobs so as to reduce the error at the output. Very simple concept, just gradient descent. So the cool thing is that we can assemble those modules in all kinds of complex configurations, and all the tools, the software tools now that are available for deep learning do this automatically. So you assemble your network, and automatically the system will know how to compute the output from the input and how to backpropagate gradient through it. So you don't have to figure out how to compute a gradient. So there's a lot of kind of practical tricks, which I'm not going to go through to make this work in practice. There's a lot of literature on this. But instead, I'm going to talk about a particular type of model that's become very, very popular, and that I contributed to proposing back in the late 80s when I was at Bell Labs, called convolutional networks. I call them ConvNet. A lot of people call them CNN, for convolutional neural net. I don't like using this acronym because if you type CNN on Google, you don't get neural net things. You get random news. So I prefer to use that. But many people, particularly in the computer vision community, call them CNNs. Okay, so that's a depiction, an animation that shows the internal working of a convolutional net for recognizing handwriting, handwritten digits in this case. So a convolutional net, again, is composed of layers. Each layer is divided into planes. Each pixel here corresponds to the activation of a particular unit in one of those planes. And the gray level corresponds to how activated the unit is. And each unit in one plane looks at a small neighborhood on the previous plane. And as you go up the layers, there's two types of layers, what we call convolutional layers and pooling layers. And they're kind of alternated. So this is a convolutional layer between here and here, and then a pooling layer, then a convolutional layer again, and then a pooling layer, etc. And as you go up the layers, the representation is more and more abstract, more and more invariant to irrelevant transformations of the input that don't change the nature of the object. And so let me go a little bit into the details of how this works. Basically, you have an input. You take a set of weights, which you can think of as kind of a little patch of coefficients. This is the sort of linear operation, if you want. And you compute the dot product between those weights and a neighborhood of pixels on the previous layer. And that gives you the value, the corresponding value here on the output. And then you take this neighborhood and you swipe it over, always using the same set of weights. So the operation to go from here to here using this little set of coefficients is called discrete convolution. I'm sure a lot of you have heard what that means. It's kind of a mathematical definition of what a discrete convolution is. And then this filter is going to be learned, and every layer is going to have several of those filters so that an input is represented by sort of different filters. Those kind of can be seen as detecting particular motifs, very simple motifs on the input. Okay, then the next layer up is what's called pooling. So the pooling layer essentially takes the average or the max of a bunch of activities in a local neighborhood, and then produces this on the output. But then this neighborhood is shifted by more than one pixel, so in such a way that this map has lower resolution than the previous one. And then you repeat the process. So each of these guys is the result of applying one of those convolution kernels to each of those planes here. They're called feature maps. So you convolve each feature map here with a different convolution kernel, add up the result, and then pass the result through a nonlinearity, and then again pooling, and then convolutions again, etc. So you train this with backpropagation. It's relatively easy to figure out how. And eventually, when you train the machine to classify digits, it figures out which values those filters should take, those convolution kernels should take. Here's a depiction of maybe a little animation of how this works. These are 3 different planes, 6 different kernels, and 2 output maps. And so this output map is a result of convolving all those 3 input planes by those 3 convolution kernels, adding up the result and writing the result in the corresponding map on the output. This is an animation that was produced by Andrei Karpathy, who is a student at Stanford. This idea, this kind of architecture actually comes from neuroscience. There's classic work in neuroscience from the 60s where these two guys, Hubel and Wiesel, they actually won the Nobel Prize for this, proposed an architecture for the kind of low-level visual cortical areas. And what we call convolution, the units in a kind of a convolutional layer, they call that simple cells. And then the kind of pooling layer, they call that complex cells. And back in the 80s, a Japanese gentleman by the name of Kunihiko Fukushima kind of proposed a model called the neocognitron that kind of used this idea, and he demonstrated that the system could actually do recognition with some invariance, but he didn't have the backpropagation algorithm, so he had to use some sort of complicated unsupervised learning algorithm that was very unstable. He was interested in kind of modeling vision, really. So my contribution to this in the late 80s was to essentially build those architectures and train them with backprop. And that resulted in the convolutional net, which basically you can think of as a succession of stages composed of perhaps a normalization that's kind of optional, those filter banks, those convolutions, pointwise nonlinearity, and then feature pooling, and you repeat this module multiple times. Here's kind of a small video that I might show you. This is a younger version of myself at Bell Labs, putting my phone number, no longer operating, under a camera, hitting a key with my finger, and then those characters are isolated by the system's very simple image processing, and then fed to this neural net that does the recognition. This was this video was produced around 1992, 1993. I can't remember the exact date. At the time, the standard PCs of the time had 386 Intel processors, which were incredibly slow for floating point computation. So we actually had to implement this on a special board that contained a DSP, a digital signal processor, capable of the absolutely unbelievable speed of 20 megaflops. Modern GPUs can do 10 teraflops, right? So, but that was kind of pretty cool. This is Donnie Henderson, or lab engineer, and Rich Howard, who was the director of the organization my department was in. So this is, early 90s, more than 20 years ago. So one thing that we discovered pretty quickly is that we could train those convolutional nets to recognize individual characters or individual objects. But once we trained them to recognize individual objects, we could apply the convolutions on larger images, perhaps that contain multiple objects, and then just replicate, apply the convolutions on larger images. When you convolve a larger image with the same convolution kernel as you had in this one, you just get a bigger image on the output. So if you view every layer as a convolution, what you get is basically a whole series of convolutional net, each output of which is influenced by a small window on the input of, in this case, 32 by 32 pixels. And so basically it very cheaply allows you to apply a convolutional net with a sliding window over a larger image. And that allows you to recognize multiple objects without even paying attention. So here's an example of how this works for handwritten digit recognition, where here we have all those kind of successive convolutional nets applied with a sliding window on the input. It's very cheap to do. What's displayed here is the highest scoring category within that window. And then a very simple post-processing kind of pulls out which objects are actually present, that if they have two 5s that are, or two 3s that are detected at the same place, it probably means it's actually the same digit. So the crucial aspect of this is that allows us to do object recognition without prior segmentation. Before that, in the classical way of doing pattern recognition, you had to isolate every object before recognizing them. And now what we could do is basically just recognize multiple objects like handwriting, handwritten words or things like that. So pretty soon, that's kind of a fun example here, where kind of a stroke can be linked with other strokes depending on which location it's based on. So there's no explicit segmentation, it's just a convolutional net doing the job here. Eventually we built a system to actually read checks out of this technology, which was deployed very widely across the world. And by the late 90s, this system of this type using convolutional net was reading 10 to 20% of all the checks written in the US, the bank checks written in the US. So it was very successful. It was used in Europe in sort of various automatic teller machine. It was actually the first company to buy the automated teller machine with the check recognition system in them. It was a French bank. It was the Crédit Mutuel de Bretagne. back in the 1995 or something. So eventually we figured out, of course, this could also work for natural images, not just digits. Of course, we had to have computers that were a little faster for natural images, but it was not very different. So eventually we figured out, we could train a system to light up when there is a face in it and not light up when there is no face, and then swipe it over an image at multiple scale to detect all faces. This is actually my grandparents' wedding. And this worked pretty well. But those results were basically just completely ignored by the computer vision community. So later, in the late 2000s, we started to think about sort of more challenging problems using convolutional nets, particularly things like what's called semantic segmentation. So semantic segmentation is labeling every pixel in an image with the category of the object it belongs to. So, a door, building, sidewalk, road, tree, sky, etc. So it's kind of the ultimate vision problem, if you want. And for this, we used a multi-scale convolutional net, which kind of, essentially decides of the category of every pixel in the image, again using a sliding window. But you need kind of a large context window to be able to decide what a pixel is. So a gray pixel, can be the road, can be the sky, can be the side of the mountain, can be the shirt of the guy here. It can be a number of different things. And so we feed the convolutional net with multiple versions of the same image at different scales, kind of a pyramid if you want, and it's the same convolutional net that is applied to all of those things. And then we kind of upsample the feature maps coming out of the low resolution networks, have a couple more layers, and then train the whole thing end to end to classify every pixel with the right category. So what you need to train a system like this is a data set of images where every pixel has been labeled, which of course there aren't many of those. The data sets that we use for this had only something like 2,000 or 3,000 images, pretty small. But it works really well. With a little bit of post-processing, we had very good performance with that system. In fact, we beat the state-of-the-art. This was around 2010, 2011, on 3 different data sets, and also with a system that was 100 times faster than the second best, running on a regular laptop. We submitted this to the CVPR conference, the Computer Vision conference, and in 2011, and the reviewer comments were, "What the hell is a convolutional net?" They just did not believe the result. They just didn't believe, it's double blind, so they didn't know who it was, and they just didn't believe the result. They said they thought it was either fake or, a mistake or whatever, and they had no idea what the convolutional net was. Eventually, we built a system that could do this in real time. I'm going to show you a video of this. So it could do this at about 20 frames per second, where we could grab a kind of panoramic image and kind of stitching so it's a guy from a lab riding a bike. He's got a helmet with USB cameras on it, so it looks like horns. And basically it labels every pixel. There is some mistakes. It's kind of stupid sometimes, but it sort of works. And again, it's only trained on something like 2,000 or 3,000 images. Sometimes, so this is in the middle of Manhattan, in fact, the NYU campus, and sometimes it classifies some of those gray areas here as desert or sand, beach, basically, desert. Middle of Manhattan, there is no desert or beach I'm aware of, but but it seems to work okay, reasonably well. So this is sort of more directly related to robotics and maybe of more interest to some of you. We kind of use this technique for labeling every pixel in an image to build a vision system for a mobile robot, a robot that drives itself in nature. So not for driving on roads or anything, or inside, but outside. And so for things that are nearby, you can use stereo vision to figure out whether something sticks out of the ground and is likely to be an obstacle, or whether something is flat. But stereo vision only works up to about 10 meters. Beyond 10 meters, stereo doesn't work. You don't have enough baseline between the cameras for the parallax to work. And so we trained a convolutional net to label every pixel in the image as to whether it's traversable or not, using labels produced by stereo, actually. But then we can use it, we can apply it to a single image. And the thing can really do a good job at figuring out what obstacles in a distance are, and that here there's probably a thing you can go through, and here you can follow the path and things like that. So that works pretty well. It was a convolutional net, relatively small, running in real time on something like a Core Duo, vintage 2006 CPU. So nothing very, very fast. But really, one of the problems that people were interested in computer vision was the ability of recognizing objects. So things like, object categories. But back in the mid-2000s, the data sets for recognizing objects were very small. So something like the Caltech 101 had 101 categories, but only 30 training samples per category. It's a very, very small data set, 3,000 images. And there's no way you can train a convolutional net to do a good job with so few examples. And so we tried to do that, and we were getting really awful results. Something like, half of the accuracy that more classical approaches would produce. Eventually, we almost matched the sort of non-learning based system, but we never kind of broke records with that. And the reason was simply that the data sets were too small. And then in 2012, two things happened. One, a data set was proposed, was made available called ImageNet, which has 1.2 million training samples. And the second thing is, it became easy to get our hands on GPU cards that were capable of over 1 trillion operations per second, 10 to the 12 operations per second. And so this data set had 1.2 million training samples, 1,000 categories, and you had to use very large convolutional nets and GPU implementations for that to work. And the first people to kind of succeed in doing this, if you want, were our friends at University of Toronto in Jeff Hinton's group, Alex Krzyzewski and Ilya Sutskever, who were students with Jeff Hinton. And so they implemented a convolutional net on the GPU and then figured out how big it had to do for this to work. And they got amazingly good results. It was a very large network with something like, almost 1 billion connections, several hundred million parameters, 8 layers or something like that. Since then, people have proposed networks that are much bigger and have many more layers. And the interesting thing is that this system was able to get error rates on the order of 15% error on the ImageNet dataset, top 5, which means an error. You count an error if the correct answer is not in the top 5 that the machine proposes among the 1,000. And the current state of the art before that was actually more like 26% error. And so it was such a huge difference that people in the computer vision community started to pay attention to convolutional net and say, look, this works really well, and there's no way we're going to be able to catch up. So we're all going to switch to using convolutional net. So only 1 year or 1.5 years after we would get a review on the paper saying, what is a convolutional net? People basically starting to switch to using convolutional nets, and basically convolutional nets took over the world. The error rate went down really quickly after that. A couple of years later, now we are down to something like less than 5% error actually on this data set. And this is the non-neural net kind of version. This was the first convolutional net, and then the next year almost everybody used convolutional nets, and then the year after that there was nothing else left. And every time the error rate decreases. So there's very, very quick progress brought about by just a lot more people kind of working on this and having ideas. And people have proposed architectures that are kind of very strange, and they tend to become deeper and deeper. So the old convolutional net I showed you from the 90s had 5 to 7 layers. The AlexNet had 10 or so. VGG, which was proposed the year after that by Oxford, had 20 layers or 19 layers. GoogleNet, which won the competition the same year, had a ridiculously large number of layers with this called Inception architecture, which is kind of a little funny. And the latest one, ResNet, which was proposed by Kai-Ming He from Microsoft Research Asia, has 152 layers. And it's got this kind of funny architecture where there is sort of bypass connections that allow basically every layer is kind of by default the identity function, and the layers sort of modify this identity function to do something interesting. Most of the layers actually don't do much, but it allows the system to kind of be robust to layers not doing much. So there is sort of an inflation of number of layers, if you want, in those years. And it's interesting to see, so you start from a random initial conditions, and what I'm displaying here are the filters at the first layer, the convolution kernels, as the learning proceeds. And they start from random configurations, and they eventually kind of differentiate themselves and kind of end up doing center surround, oriented edges, gratings, etc. And we get this hierarchical representation of the world basically directly out of it, just training from data. And so one thing that people have tried to use convolutional net for now, since in the last 2 or 3 years, is a lot of different things. Like, for example, producing captions for images. So here is an image. Here is a description of this image by a human person. Here is kind of what the system produces. This is a system built at Facebook, but there's probably 10 different labs that have similar systems. It says a man wearing skis on the snow, a man riding a skateboard on a ramp, a woman holding an umbrella. It's pretty decent descriptions. It's actually less impressive than it seems, because the set of possible sentences that are present in the data set is actually relatively small. So it's relatively easy for the machine to produce a sentence that kind of makes sense. But so it's not. It doesn't completely solve the problem. There's a lot of images that you show to the machine, and it kind of produces complete garbage. But it works well enough that there is a service that was deployed by Facebook just last week that essentially produces description of images for the blinds, for visually impaired. And so if you're blind and you want to use Facebook, there's basically a system that will just vocalize a description of the images that are posted by your friends. It's pretty useful. It's also, of course, useful for kind of generating indices and doing image search and stuff like that. So one application that also is used at Facebook is for face recognition. So if you live outside of Europe, when you post a picture on Facebook with your friends' faces are recognized, and they are alerted that a picture of them has been posted, that you posted a picture with them. This feature is very useful to a lot of people, but it's not activated in Europe, just because people in Europe are kind of not entirely comfortable with the idea, so we just don't activate it. But basically, it's a convolutional net. So we take a face and we locate some of the key features of the face. We map kind of a 3D-ish model on this, which allows us to kind of rotate the face as if it was frontal. So even though the face doesn't look directly at the camera, here we can sort of transform it so that it's as if it looks at the camera. And then we feed it to a convolutional net, which is trained on lots and lots of different faces, and it works amazingly well. It actually uses a technique here called metric learning. So metric learning is a technique by which you show 2 images of the same person, you run them both through the convolutional net, and the convolutional net produces 2 vectors, and you say, I want those 2 vectors to be the same, or very similar, okay, because they're 2 images of the same person. And then you run 2 images of different people through the convolutional net, and then you tell the machine, I want those 2 vectors to be different from each other, to be far away from each other. And what you get in the end is a convolutional net that produces vectors corresponding to faces where Euclidean distance corresponds to identity. So the distance of one vector to another basically determines how likely the corresponding images are from the same person or not. And that works really well. This is a technique that was proposed by 2 of my students, Sumit Chopra and Raya Hetzel, back in 2005, 2006, and we called it Dr. Lim, dimensionality reduction by learning an invariant mapping. It sounds like a James Bond movie, like Dr. No or something, but it works pretty well. So one application that people have been interested in a lot is not just recognizing objects, but also locating them. And there is a very simple way to do this. The same way I explained we can do face detection is by taking multiple resolution versions of the image, swiping the network with a sliding window over it, and then what we get is a heat map. This is the heat map for the category bear. And so all the detectors that see the bear or part of the bear kind of turn on at this scale. And they turn on less at the finer scale. And so you can use this to kind of locate the bear. There's another trick to kind of get the machine to not just produce a detection for the bear, but also an estimate of where the bounding box for the bear would be. So 4 of the outputs of the network are actually kind of a prediction of a bounding box. And it's trained simultaneously with the categorization. And so eventually you can combine all those things to kind of identify and locate the bear. And it works pretty well. And you can use this, of course, to do things like identify the pose of a body by training detectors to detect shoulders and elbows and wrist and head and things like that. But this has made a lot of progress over the last year with a technique we call deep mask, where we train a convolutional net not just to identify the main object in the picture, but also to generate a mask of that object. So here the main object in the picture is this elephant, and we kind of generate a mask of this elephant. So that requires to have a data set where every object has been outlined, but there are data sets of this with a few examples that you can use. So those are examples of candidate objects that have been generated. And then you kind of integrate this into a very complex set of multiple neural nets, which I'm not going to go into, that you train on the gigantic machines with 8 GPUs on them, that you stack in a rack. It's called Big Sur. It's kind of our deep learning engine, if you want, at Facebook, using distributed stochastic gradient algorithm, something called EASGD. And you get things like this. So this is an image, and that's the result produced by the system, where it recognized the boats here, out there, the person, the skateboard. There's a piece of a person here that's recognized, cell phones, laptops, etc. Even if there is, chicken wire in between, you get the people that are detected properly, even if you see the top of them. That's a pretty amazing one, I think. So this guy actually is detected properly. Frisbee is identified. Broccolis, this Chinese dish. You can, if you don't like broccolis, you can have, an owl kind of pick out the broccolis out for you. There are mistakes. That's not a baseball glove. And those are kind of semantic mistakes that a machine could perhaps figure out if it had kind of a broader semantic context, but this is just a vision system. That's my favorite example. So there's a bunch of sheeps, and you can count the sheeps. This sheep here is broken in half, but it's lamb chops, donuts, animals, who are in the business of hiding themselves. Various items. So this works, right? I mean, it's not like vision is completely solved, but this is, things that you would have asked, vision researchers 5 years ago. How long is it going to take for us to be able to do this? They would not have said that we would be able to do this by 2016. So this sort of accelerated progress because of deep learning and because of all the people kind of jumping on the bandwagon and kind of inventing new techniques. So the cool thing also is that people have been trying to use convolutional nets for speech recognition, and this works really well. This is some work my NYU lab did in collaboration with IBM for speech recognition. And it's a multilingual convolutional net that is trained to basically do the acoustic modeling in speech recognition for Kurdish and Kazakh and Lithuanian and a bunch of other languages. And the cool thing is that there is not a huge amount of data for each of those languages, but because the bottom layers of the network are shared among all languages, it learns features that are generic to any speech, regardless of language. It's pretty cool. And it's a convolutional net. If you talk to your Android phone or quite possibly your iPhone, the system that does the mapping of your speech to kind of sound categories is a convolutional net. ConvNets are everywhere, or soon will be. People are building chips for them. This is a picture of Jensen Huang. He's the CEO of NVIDIA, the GPU company. And NVIDIA has been embarking on a big project to actually build embedded systems for self-driving cars, robotics, and things like this. One of the things I'm rooting for is that in your next version of whatever robot you guys produce, you put one of those things in it. Because that's the only way your robots are going to have powerful enough sensor processing for doing things like vision and speech and dialogue systems and language understanding, perhaps even translation and stuff like that. Basically, those machines have the required power to do this. They have enough power to do basically self-driving cars. So they certainly have enough power to might be a little too big for a robot for now, but maybe in a Pepper or something like that. But pretty soon, those guys are going to build chips for this that are supposed to be targeted for mobile devices, and those will, be appropriate for a robot. compact and cheap enough. So what NVIDIA is doing is that they are actually providing not only hardware platforms but also software platforms to run algorithms very similar to the one I talked about earlier. In fact, this is directly inspired by the semantic segmentation system I was talking about earlier. Another company that's very active in this is Mobileye. So this is an Israeli company, and they build special purpose chips and software and some kind of black boxes that car manufacturers put behind the windshield to kind of look out the window and essentially provide self-driving capabilities. So if you are lucky enough to have a Tesla has a self-driving thing that you can activate by just pushing a button, and it uses a convolutional net, and it does operations of this type where it figures out, what is traversable, very much like the robot I showed you earlier, and figures out all the, detects all the people and the cars and everything. So another thing that people are working very actively on is convolutional nets applied to medical image analysis. This is probably going to have a big impact on radiology because some of those systems can do things like identify tumors more reliably than most radiologists. And so the combination of an expert radiologist with a system of this type will probably be a very good thing for public health. So to give you an idea, so companies like Facebook, Google, Microsoft, Baidu, all the big players, IBM, use convolutional nets in a big way for image recognition. So to give you an idea of the scale, every day, Facebook users upload anywhere between 800 million and 1.3 billion photos on Facebook. This is every day, roughly 1 billion a day. And this does not count WhatsApp, Instagram, and Messenger. It's just Facebook. All of those images go through 2 convolutional nets within 2 seconds. One convolutional net identifies objects in the image, basically generates something like 2,000 different tags that allow us to basically know what the content of the photo is. And the other convolutional net does face recognition. That one, of course, is not activated in Europe, as I said before. So it's not 1 billion, it's maybe 800 million or something for that one. But you can imagine, given the size of those convolutional nets, you can imagine the kind of infrastructure that's required for it. Also, there is a lot of work in sort of the optimization of running those convolutional nets on the servers to actually save a lot of computation. So this is a very challenging problem. A lot of effort is devoted to this. So pretty soon, thanks to ConvNets and deep learning, we'll have self-driving cars, medical imaging that works, augmented reality and mobile devices, and smart cameras, robots, toys, things like that. But that will require a lot more compute power than what you currently have in your robots. So if I have one request is put a GPU somewhere in your robot, so we can actually run big algorithms. Okay, so a big area of research nowadays is the use of deep learning in natural language understanding and natural language processing. And it's a very interesting development because until recently, NLP is one of the areas where deep learning was kind of, people were hopeful, but deep learning hadn't, taken over completely, hadn't kind of beaten more classical systems, if you want, for typical tasks. And that's changing just about now. So there's a technique called word-to-vec that some of you may have heard of, which is basically an unsupervised learning technique that learns to associate a vector to each word. And it's done by basically taking a sentence from a piece of text or a series of successive words from a piece of text and training a machine to map those words to vectors, and then taking this combination of those vectors to predict what the word in the middle is. So you just train a classifier as if it was a classifier with, say, 100,000 categories, the size of the dictionary. Tell me what word would be in the middle here if you read all the words on the side. And in the process of doing this, the system kind of learns really good representations for word. This was actually pioneered by Yoshua Bengio at Montreal and Ronan Colobert and Jason Weston, where they were at NEC back in the late 2000s. Both of these guys are now at Facebook. And then there is a technique called word-to-vec invented by Tomasz Mikolov, who at the time was at Google, who is now at Facebook, also to which is this technique. And you get this kind of amazing result that if you take the vector for Tokyo and the vector for Japan, and you subtract the vector, do Tokyo minus Japan if you want, you get a particular vector. And if you do Berlin minus Germany, you get another vector. And those vectors are pretty much the same. So Tokyo minus Japan equals Berlin minus Germany, which allows you to do something like Tokyo minus Japan plus Germany equals Berlin. Or Tokyo is to Japan as Berlin is to Germany. Things like that. So analogy through algebra. And this is very important because a lot of us have been thinking that reasoning should not be done through logic, or rules, but should be done through continuous mathematics. And the reason for that, basically, instead of symbols, you have vectors. Instead of logical operations, you have continuous mathematics operation, like linear algebra and things like this, neural nets. And the reason for doing this is now every operation the machine does is differentiable. You can propagate gradient through it, and therefore you can train the machine to do the right set of reasoning, if you want. So, substituting symbols, changing symbols by vectors, in fact, is perhaps one of the hopes that will allow us to train machines to do reasoning. So, for example, we can use this to build question answering systems where, a data, a knowledge base is, for example, represented by a knowledge graph, which is a bunch of entities like, George Clooney and, whatever her name is, Preston, that's her wife, his wife actually. And the relationship is, they're married with each other. Clooney is also an actor, and he played in Ocean 11, all that stuff, right? So there's a technique where you can take two entities and a relationship, represent them as vectors, and then combine those vectors through a trainable function to produce a single vector that represents this whole relationship, if you want. And then simultaneously, you can also take a sentence, which would be a question, for example, and then using those word embeddings, you get a sequence of vectors that correspond to the vectors for each of those words, and then you can train a function to map this to a single vector. And what you're going to do is train these mappings in such a way that whenever you have a vector for a question, the vector for the corresponding answer is nearby. So this is the same trick that we use for face recognition. Take a question, take the corresponding answer, run them through neural nets, and train this neural net so that the output vectors of the question and the answers are nearby, and then take another answer that does not correspond to this question, and then move them away. And this actually works. So you can build question answering system based on this, where the similarity basically is the dot product or Euclidean distance between vectors on the output. Another example is an idea to do translation, which is sort of an old idea, but it was kind of really demonstrated in a big way by Ilya Sutskever, who was at the time at Google Brain. And he used what's called recurrent neural nets using LSTM, a particular type of recurrent neural net, in such a way that you can feed a sentence in one language to the recurrent neural net. And what the neural net does is that it accumulates the meaning of that sentence into kind of its state vector. So this is kind of time going this way, if you want. And so the collection of those vectors represents the content of the sentence, the meaning of the sentence. And then that vector is fed to another recurrent net, which is trained to produce sentences in French from this input. And you train this whole thing end-to-end with pairs of sentences in English and French, just doing backprop. It's called backprop through time because it's a recurrent net. And this, amazingly, actually works. It's pretty gigantic neural net, but it actually works. And it approaches the performance of more traditional sort of phrase-based statistical language translation system. More recently, people at University of Toronto, in fact, in Yoshua Bengio's lab, in fact, Kyung-Yoon Cho now is an assistant professor at NYU, New York University, proposed to kind of simplify this architecture while making it more complex but smaller using what's called attention mechanisms. I'm not going to go into the details of what this is, but they managed to really kind of get really good results with much smaller recurrent nets than what Ilya Sutskever was able to do. And more recently, they get really good results. More recently, Chris Manning kind of re-implemented this. So he's at Stanford with a student. Re-implemented this method, attention-based encoder-decoder recurrent neural net for translation, and actually won a translation competition with that. So now we are in the situation where the best system in the world to do translation actually is a recurrent neural net trained end-to-end. And that's a very important event because that means Now it's over. Translation is going to be done by neural nets. They are a little expensive now to run on sort of practical services to scale them up to all the users for Google and Facebook, but it's going to happen within the next year, most likely. So a generalization of this is something called memory augmented network. So it turns out recurrent nets are really bad at remembering things. And I'm not going to go into the details of what that is, or of why that is. Yoshua Bengio had a theoretical paper about this in 1994, but basically recurrent nets, despite the fact that they are designed to remember things from the past, a long time in the past, they are actually not very good at this. And so one proposal which goes back quite a bit of time is this LSTM architecture, long short-term memory, which was proposed by Sepp Ohrheiter and Jürgen Schmidhuber in Switzerland to kind of essentially allow recurrent nets to remember things by default, so that things would not kind of vanish, information would not vanish by default in a recurrent net. It was a pretty cool idea. It's actually used pretty widely in those translation systems, among other things. But a more recent proposal is by Jason Weston, Sumit Chopra, and Antoine Borde at Facebook called the Memory Network. And another proposal by Armand Joulin and Tomasz Mikolov, also at Facebook, called Stack Augmented Recurrent Nets. And then a proposal that's slightly different, but with the same kind of motivation, called Neural Turing Machine, proposed by DeepMind just about the same time. In fact, this paper, I think, came out on arXiv 3 days after that one. So the idea was in the air, and everybody was working on it, basically. And the idea is to have a recurrent net that's augmented by an associative memory. And the associative memory looks very much like kind of a soft RAM circuit, if you want. So basically, you take a vector. It's viewed as an address in a memory. And so that vector is compared with a bunch of keys, kind of like in a hash table. And the way you compare them is using a dot product, right? So you do the dot product between this vector and all those vectors. This is like a matrix vector multiplication, basically. You get a bunch of scores. You pass that through a softmax. So a softmax is this operation. It takes every value, passes them through an exponential, and then normalized by the sum. So you get a bunch of numbers between 0 and 1 that sum to 1. Those are coefficients. And then to read the memory out, you compute a weighted sum of the values in the memories, weighted by those coefficients. So if this vector is close to, aligned with one particular vector, let's say this one, and not aligned with any of the other ones, let's say it's orthogonal to all the other ones, then this score will be 1, the other one will be 0, and what will come out of the memory is just this vector. So that's just like a hard RAM circuit, if you want. But because it's soft, you can backpropagate gradient to that, and you can train this memory to actually remember things, store things that are useful in the context of a complex process. So there's an architecture called the end-to-end memory network, and I'm not going to go into the details of how this works, but basically it's a kind of an unfolded recurrent net that accesses this memory multiple times. And if this memory contains facts about a particular situation, like a sequence of things that happen in a story, then a system like this can be trained to answer questions about that story. And a very nice example of this is this, where you have here a 15-sentence version of the Lord of the Rings. It's basically all the events that occur in Lord of the Rings that are of any interest. And then you don't want to read the last 4 if you haven't read the books or seen the movie, because it's a spoiler. But then you get the machine to read this. It's going to store all those facts in its memory, and then you can ask questions like, where is the ring? It's in Mount Doom, and where is Bilbo now in Grey Heavens, etc. So it's a really cool thing. We're not to the point where we can read all of Wikipedia and then answer any question contained in Wikipedia. But that's a pretty far away goal, but that's one of the things that we might be able to do in the next several years. And this thing can answer a fairly complex question, like Brian is a lion, Julius is a lion, Julius is white, Bernard is green. What color is Brian? If you think that all lions are white, then Brian is white. Or Mary went to the den, Mary went back to the kitchen, John went to the bedroom, Mary discarded the milk. Where is the milk? Where was the milk before the den? Maybe in the hallway. The answer is actually not contained in this thing. But so things like that systems like this can do. And now there's a lot of work on actually training recurrent nets augmented with memory, possibly, to actually learn algorithms. So you demonstrate an input and an output, and there's some algorithm that produces the output from the input, and you show several examples, and the machine figures out what the algorithm is using backprop. It works in simple situations, but it's kind of pretty amazing you can do that. Okay, so now I'm getting to the future. So what are the obstacles to progress in AI? The main obstacles, and these are, some of those things are very personal opinions that may not be shared by the entire deep learning or AI community. So in my view, I think there are kind of three things that are missing, three obstacles. The first one is, I just talked about it, how to integrate deep learning with reasoning, attention, planning, and memory. So this is things that are, the projects I just mentioned are basically along this direction. Of course, this would be very interesting also for robotics and control and things of that type. Second one is integrating supervised and unsupervised reinforcement learning into a single algorithm. Right now, those are kind of different modalities and different algorithms, and I don't think it should be that way. And the third one, which I think is the most important one, is finding effective ways to do unsupervised learning, or rather, I should say predictive learning. When I say unsupervised learning, the kind of general public, has the wrong idea about what that really means. So it's like, you mean robots can kind of learn by themselves and will take over the world and things like that? No. Anyway, so basically there are those three types of learning. Reinforcement learning, admittedly, this is a very narrow definition of reinforcement learning, but it's the definition I will use, is the situation by which you tell the machine whenever it makes an action, whether this action was correct or not, but you don't tell it what the correct action is. So if the machine has a spectrum of possible outputs it can produce, the only thing you're telling it is whether the output it produces was right or wrong. And maybe, it's some sort of continuous reward that you give it. But basically, the machine only gets a scalar out of the environment or out of the trainer. The second modality, of course, is supervised learning, where you tell the machine what the correct answer is. So implicitly, you're telling it, you get rewarded for this output and you don't get rewarded for the other outputs. And then the last one is unsupervised learning. That's basically predicting, learning to predict how the world works, observing the world and, getting the machine to tell you what's going to happen next. And the bad news is that most of the learning that humans and animals do is unsupervised. So in a way, if intelligence is kind of a cake, like a forêt noire cake or something like that, Black Forest cake, unsupervised learning is the génoise, is the bulk of the cake. Supervised learning is the icing on the cake because the machine doesn't get a huge amount of information from the environment. And reinforcement learning is the cherry on the cake because there's very, very little information the environment provides to the machine in that case. And so we are in the embarrassing situation where we know how to make the icing and the cherry, but we have no idea how to make the cake. And that's kind of embarrassing. It's sort of like, physicists who study cosmology and they can't tell you what 95% of the mass in the universe is. It's dark energy and dark matter, and they have no idea what it is. It's kind of the same situation here. Unsupervised learning is the dark matter of AI. All of the things we learn about the world when we're babies, we learn unsupervised. We learn the world is three-dimensional. We learn that objects exist even if we don't see them. We learn, that's called object permanence. We learn that certain things cannot happen in the world, and if they do happen, they are either scary or really funny. This guy kind of is rolling on the floor from this magic trick. We learn how the world works by just, observing it and predicting what is going to happen next. And that's really what unsupervised learning is about. And I think it's the secret to acquiring common sense. So we don't have machines that have common sense. If you close your eyes and I say, Bernard, John, whatever, Bernard picks up his bag and leaves the room. You can infer that a lot of things have to happen. Bernard probably has to stand up and extend his arm, open his finger, pick up his bag, walk. He's probably not going to fly. He's probably going to have to go to the door and maybe open the door. He's not going to go right through the door. And so there's a lot of things because you know how the world works. There's a lot of constraints about the physical world that you've learned by just living in it. And that's what allows you to kind of fill up the blanks with just a few words. And that's what we can't do with machines today because we don't know how to do unsupervised learning. So unsupervised learning, basically the technical problem there is the following. We observe the past, we can predict the future, but the future, there's a lot of different things that could happen, which I symbolize by this kind of manifold of possibilities here. And then you let time pass by, so you make a prediction here, and you let time pass by, and it turns out the world does this. What you predicted was perfectly fine. It was on the manifold of possibilities, but the world just happened to do this because of things you could not predict. And so what you want is you want a function, you want a way of training a machine in such a way that if it makes a prediction that is on the set of plausible things that could happen, even if it's not the thing that actually happened, you don't want to punish it for it. You want to say, okay, it's still okay. If I put this thing on this table and I let it go, it's probably going to fall. And from the distance you are, you probably can't tell which way it's going to fall. But you're going to predict it's going to fall. So let's say you predict it's going to fall to the right, and in fact it falls to the left. Your prediction was still correct, technically. So how do we do this? That's basically the technical problem we have to solve. And it's not entirely clear how to do this. One approach is what's called adversarial training, and that's what I'm going to end with. So adversarial training is this really, really cool idea, and it's very new, and a lot of people are really excited about it, is you basically train the loss function. So essentially you don't know what this manifold looks like, so you need a trainable function to tell you whether a point is on this manifold or not of possibilities. And that's going to be another neural net. So now this is this neural net. This neural net is trained to produce 1 or 0, or some number. And if the number is 0, that means whatever is fed to it is on the manifold of possibilities. If it's not, then it's not. And the way you train this system is that you have a training set of images, and you train the discriminator to tell 0 because those are real. But then you also have another neural net generating images from a set of random numbers. And whenever it produces an image like this that you show to the discriminator, you tell the discriminator, tell me it's fake. Okay, so produce a large output. But the point is the generator actually trains itself to fool the discriminator, and it can do this by being fed the gradient of the output of the discriminator with respect to the image. So it can adjust the image so as to fool the discriminator as much as possible. And if you do this, you can generate images that are absolutely amazing. So these are, this is work by Alec Radford and his collaborator. They're in a startup in Boston, and Sumit Chintala, who is at Facebook. And basically what they train is some sort of convolutional net-like network to generate images, not recognize them. You feed it random numbers. It's been trained on images of bedrooms. You feed it a bunch of random numbers, and out comes an image of a bedroom. And those are generated images from those random numbers. And they look perfectly fine. They all have a bed. They all have windows. They have dressers. They have things in it that look like things that should be in a bedroom. And it's completely amazing that it works at all, but it works really, really well. So that's very impressive, very surprising. They put the code in open source on GitHub, and then people kind of trained it on random things like manga characters. So these are artificially generated manga characters by interpolation in this feature input random numbers. And so by continuously varying them, you can generate manga characters that kind of change continuously. You can do things similar to what we did with Germany and Tokyo and Japan, but now with images. So you take the vector corresponding to a man with glasses, subtract the vector of a man without glasses, add a woman without glasses, and you get a woman with glasses. I mean, that's just astonishing that it works. And you can do this also with physics. I'm going to skip this because I'm out of time. But the last thing I'm going to mention is how you can do this to train what we call forward models of the world, which are systems that basically predict what's going to happen in a video. So you train basically a multi-scale convolutional net to observe a few frames in a video and then train it to predict what's going to happen next in the video. And if you train it supervised with least square or something like this, you get very blurry predictions. They're blurry because there's a lot of possible things that could happen in the world, and the best thing the machine can do is predict the average of all the possible things that could happen, and that's just a blurry image. So it doesn't work. But if you use adversarial training, so these are the 4 frames that are observed. This is the ground truth. This is what actually happened in the video. This is what the system predicts if you train it with least square. And this is what the system predicts if you train it with this adversarial training technique, where the cost function basically is trained as part of the process. And that works kind of decent. You can predict where billiard balls are going to go, and you can do things like that. So This is my last slide. So here, the first 4 frames of very little animation here is comes from a real video, and then the ones that are surrounded, the 2 frames that are surrounded by a red frame here are actually predicted by the network, and they look pretty decent. You know, this guy keeps moving, this thing keeps moving in the right direction, this kid here keeps advancing. This is for L2 training, etc. So it starts going like really, it looks bad when you let the system predict more than a few frames. It diverges pretty quickly, but at least there is a hope there that we have an angle on this predictive learning. And we think, being able to solve that problem really is the key to unsupervised learning or predictive learning, which will allow us to get machines to acquire common sense and then get to the next step in terms of AI. And I'll stop here. Thank you very much.